The brightest galaxy ever observed in the known universe radiates with a brilliance beyond comprehension, pouring out the light of over 300 trillion suns. This single object, catalogued as W22246, though 526, outshines not just the neighboring galaxies around it, but also everything else we have ever detected in the cosmos. Its luminosity is so intense that to describe it in numbers alone is to reduce it to abstraction. Imagine not merely one Milky Way, but thousands of them stacked atop one another, each burning at maximum intensity, compressed into a single point of reference in the night sky. That is the scale of brightness we are speaking about here. For those who seek to explore the mind and universe together, subscribe, like this video, and share where in the world you are watching from. Galaxies like W22246, 0526 present not just a marvel of astrophysics, but also a profound riddle. What does it mean for matter and energy to condense into such extremes, and what hidden truths about perception, consciousness, and the nature of reality do they reveal? At first, this may seem like two separate questions, one for astronomy, one for psychology. Yet, the boundary between the outer universe and the inner one has never been entirely fixed. Both depend on the way light is measured, processed, and interpreted. Both require the mind to stretch beyond its normal thresholds, where ordinary categories begin to blur. Brightness itself is not a simple concept. In everyday life, we think of a bright lamp or a glaring sun as physical intensities that strike the eye and overwhelm vision. But in astrophysics, brightness is tied to luminosity, the total energy output per unit of time, irrespective of distance. A candle held close may dazzle more than a star across the void, yet that star produces vastly more energy. To grasp the meaning of W22246, 0526, one must learn to set aside the limits of ordinary sensory scaling. The brain evolved to adjust pupils and regulate photoreceptors within modest bands of daylight and starlight. It never evolved to grasp magnitudes like 300 trillion solar equivalents. What we call brightness at such levels is no longer a sensory term, but a conceptual one. And yet the psychological machinery used to process brightness remains inescapably human. When confronted with overwhelming light, the nervous system reacts in patterned ways: contraction of pupils, activation of the superior colliculus, and triggering of subconscious defensive responses. These reactions appear not only in physical glare, but also in imagined brightness during altered states. Hallucinations induced by fasting, meditation, or psychoactive substances often describe oceans of light, or radiant voids, that bear striking resemblance to metaphors of the cosmos. Neuroscientists such as Andrew Newberg, studying religious experiences through fMRI, have documented how parietal lobe activity diminishes when subjects report immersion in overwhelming radiance. To experience infinite light may be to feel the nervous system surrender its ordinary spatial maps. Thus, when astronomers speak of a galaxy like W22246, 0526 blazing in infrared, they are not only charting a physical object across 12 billion light-years of space, but also summoning metaphors that strain the brain's perceptual circuits. The raw numbers require translation into something the mind can hold, and the translation often takes the form of awe, reverence, or even disquiet. In psychology, awe has been shown by researchers such as Dasher Keltner to alter time perception, expand attentional scope, and dissolve rigid self-boundaries. The universe, by sheer magnitude, forces the same mental transformations that ancient rituals once did by fire, chant, or trance. Tor-6, 0526 becomes, therefore, not merely a point in a sky survey, but a trigger of altered states through cognition alone. One does not need to travel to that galaxy to be altered by it. the act of contemplating its existence, bends the pathways of attention and imagination. The mind struggles to anchor itself against numbers that dwarf comprehension. Trillions of suns, billions of light years, aeons of time. As the neural system oscillates between comprehension and incomprehension, it brushes against thresholds usually crossed only in mysticism or visionary states. This duality, the astrophysical fact and the psychological impact, is what makes the brightest galaxy such a profound subject. On one level, it is a question of matter and radiation, of dust and gas collapsing into extraordinary densities. On another, it is a mirror that reveals the limits of perception and the pliability of consciousness. The Greeks once spoke of phos, the divine light, not as a metaphor, but as an experience overwhelming enough to undo the ordinary self. Neuroscience confirms that states of sensory flooding, whether from extreme brightness, sound, or breath-induced hyperventilation, can deactivate the default mode network, loosening the ordinary boundaries of self. To look toward W22460526 is to confront a modern version of that same paradox, an object so bright that it becomes, paradoxically, invisible to the naked eye. At visible wavelengths, the galaxy is faint, shrouded in dust. Only when instruments tuned to infrared strip away the veil does its true ferocity emerge. This contrast mirrors the psychological reality of the unconscious, forces hidden beneath the threshold of awareness, visible only when the correct method of observation is applied. The brightest galaxy ever found, thus, does more than expand astronomical catalogs. It challenges both science and psychology to account for what happens when extremes of energy are placed before a nervous system unprepared to receive them. And like all thresholds, it leaves open the question of what happens when the limits are crossed, when intensity becomes more than signal, when perception gives way to something else altogether. Brightness in astronomy is not measured the way the human eye perceives it. The subjective sensation of glare or dazzle corresponds only loosely to the underlying physics of luminosity. Astronomers rely on two distinct but related concepts: apparent brightness, which is how much light reaches an observer at Earth after traveling across space, and intrinsic luminosity, which is the total energy radiated by an object per unit time across all wavelengths. The brightest galaxies known to science are not always the ones that appear most vivid through a telescope. Distance, dust, and wavelength sensitivity shape perception as much as the intrinsic power of the source itself. Galaxies shine for multiple reasons, and the source of their brilliance reveals much about their inner structure. In some cases, light comes primarily from stars. Billions of nuclear furnaces radiating visible and ultraviolet energy. A galaxy undergoing a rapid episode of star formation, often called a starburst, can temporarily blaze with the combined intensity of newly ignited stellar populations. These bursts are usually short-lived on cosmological scales, lasting tens of millions of years, but they create striking luminosity peaks. Regions like the Tarantula Nebula in the Large Magellanic Cloud illustrate this process on a smaller scale, where thousands of massive stars pour out radiation, ionizing surrounding gas and producing radiant emission lines detectable across intergalactic distances. Yet star formation alone cannot explain the extremes of galactic brightness. Observations from the 20th century revealed another mechanism, more violent and less intuitive. At the centers of many galaxies lurk supermassive black holes, ranging from millions to billions of solar masses. When gas, dust, and even entire stars fall inward toward these compact objects, the material does not disappear instantly. Instead, it spirals into an accretion disk, where gravitational energy converts into heat and radiation. Friction and compression raise the temperature to millions of degrees, generating light across the electromagnetic spectrum. X-rays, ultraviolet, optical, and radio waves. In some cases, relativistic jets channel plasma outward at near-light speed, creating additional streams of emission. This process, known as an active galactic nucleus, AGN, can outshine all the stars in its host galaxy combined. Quasars, the most radiant variety of AGN, puzzled astronomers when first discovered in the 1960s because their apparent brightness suggested objects much closer than their redshifts implied. It took decades of spectroscopic analysis, radio mapping, and theoretical work to establish that these were indeed galaxies powered by central engines of extraordinary efficiency. The conversion of gravitational potential energy into radiation near a black hole can reach efficiencies of 10% or more, far higher than the 0.7% efficiency of nuclear fusion inside stars. Brightness then becomes a diagnostic tool, revealing which mechanism dominates. A galaxy, glowing primarily by starlight, carries the spectral signature of stellar populations. Absorption lines, thermal spectra, and characteristic colors depending on the age and type of stars present. In contrast, a galaxy dominated by an active nucleus exhibits broadened emission lines, extreme ultraviolet output, and variability across timescales of days to months. Instruments such as the Sloan Digital Sky Survey and the Hubble Space Telescope have cataloged thousands of such luminous systems, each providing data on how galaxies evolve through phases of intense activity. Measuring brightness also requires instruments attuned to wavelengths invisible to the eye. The human retina is sensitive to a narrow band from roughly 400 to 700 nanometers, yet galaxies emit far beyond this range. Infrared observations reveal dust-enshrouded regions where starlight has been absorbed and re-radiated. X-ray telescopes capture violent processes near accretion disks. Radio arrays detect synchrotron emission from relativistic jets. Without these extended tools, the brightest galaxies in the universe would remain hidden, their true power cloaked from ordinary perception. Brightness is not static. Galaxies pass through phases of dormancy and eruption, shaped by mergers, accretion events, and internal feedback processes. When two galaxies collide, gravitational forces funnel gas toward the center, triggering both starbursts and black hole feeding. The combined effect is a surge in luminosity that can rival the output of hundreds of billions of suns. Over time, however, feedback from radiation and stellar winds can expel gas, suppressing further star formation and reducing the galaxy's glow. What appears as a sudden blaze on cosmological scales is often a brief, turbulent stage in a much longer evolutionary cycle. Psychologically, the concept of brightness at these scales parallels the way the human mind interprets extremes of stimulation. Studies in sensory psychology show that the nervous system adapts to constant inputs, recalibrating sensitivity to maintain equilibrium. Bright light, loud sound, or strong odor may initially overwhelm, but over time, neural circuits dampen the response. Galaxies, in a sense, undergo similar adaptation through feedback. Their own outpouring of energy alters the environment that sustains them, preventing unchecked growth. The feedback loop ensures that brightness, though extreme, is temporary. A balance enforced not by external law, but by the dynamics of the system itself. The ancient fascination with brightness in the heavens reflected both awe and caution. Cultures worldwide equated radiant objects with divine power. The Egyptian sun god Ra, the Zoroastrian reverence for fire, the Christian image of unapproachable light. Modern science translates these myths into measurable energy outputs, yet the psychological effect remains. The brightest galaxies induce the same oscillation between wonder and fear, a sense that light at such magnitude carries both revelation and destruction. To isolate what makes a galaxy bright is to trace the interaction between stars, black holes, and gas, each component capable of transforming gravitational collapse into radiant energy. But behind the physical mechanics lies a deeper tension. Brightness is never neutral. It is a force that alters its own conditions of existence, destabilizing the structures that gave rise to it. In every galaxy that reaches such intensity, a question lingers over how long the blaze can continue before it unravels the very system that sustains it, leaving a precarious threshold whose consequences stretch far beyond immediate observation.
The detection of W2246-0526 required a shift in perspective, both technological and conceptual. Traditional optical telescopes, the kind that record photons in visible wavelengths, were blind to its magnitude. Dust within the galaxy absorbed starlight and high-energy radiation, masking its presence from instruments that depend on unobscured light. To uncover it, astronomers turned to infrared observatories, whose detectors capture the heat re-radiated by dust grains after they absorb more energetic photons. This technique allowed the invisible to emerge, and with it, one of the most extreme objects ever catalogued. The Wide Field Infrared Survey Explorer, WISE, launched by NASA in 2009, mapped the sky in 4 infrared bands, each corresponding to different energies and depths of penetration through cosmic dust. Its detectors scanned continuously, identifying tens of millions of galaxies. Among them, one stood out for its staggering infrared output, W2246-0526, located roughly 12 billion light-years from Earth. At this distance, the light we receive left the galaxy when the universe was less than 10% of its present age. Its faint trace, stretched by cosmic expansion, carried information about a time when galaxies were still assembling from primordial matter. Infrared astronomy has long been central to discoveries about dusty, energetic galaxies. Instruments such as the Infrared Astronomical Satellite, IRAS, in 1983 revealed the existence of ultraluminous infrared galaxies, or ULAGs, whose brightness in infrared exceeded 1 trillion times that of the Sun. Later missions, including the Spitzer Space Telescope and the Herschel Space Observatory, deepened this view, uncovering populations of dusty starbursts and black hole-powered systems invisible to optical surveys. W2246-0526 surpassed them all, leading to its classification as the most luminous galaxy known at the time of its discovery. Confirmation required more than one telescope. Follow-up observations with the Atacama Large Millimeter/Submillimeter Array, ULMA, in Chile provided sharper resolution and measured emissions from ionized carbon in the galaxy's interstellar medium. These data revealed turbulent gas flows, moving at extraordinary speeds, a sign of the violent processes driving its luminosity. The interplay between absorption, re-radiation, and outflow traced a feedback system of staggering power, with energy channeled from the central engine to the farthest reaches of the galaxy's structure. The process of identifying an object like W2246-0526 is not as straightforward as recording a bright point of light. Astronomers must disentangle its emission from foreground objects, assess its redshift through spectroscopy, and calculate luminosity by correcting for distance and wavelength effects. Spectroscopic analysis revealed a redshift of approximately 4.6, corresponding to a look-back time of over 12 billion years. At such redshifts, light is stretched into longer wavelengths by cosmic expansion, meaning that radiation emitted as ultraviolet or visible arrives at Earth in the infrared. Instruments sensitive to these wavelengths become not just useful but indispensable. The brightness of W2246-0526 presented a paradox. Despite its immense luminosity, it remained hidden in visible surveys, a ghostly presence cloaked by its own dust. This paradox underscores the importance of wavelength in astronomy. Objects invisible in one band can dominate in another. The situation mirrors psychological phenomena in which perception depends on the filter applied. Just as selective attention can make a stimulus vanish from awareness despite its intensity, so too can dust render the most radiant galaxy effectively invisible without the proper observational framework. The discovery also highlights the role of serendipity in science. WISE was not designed to locate the single brightest galaxy, but to create a comprehensive sky map. Within that map, anomalies emerged, objects that stood apart from the statistical distribution. The brightest galaxy was not identified because astronomers were searching for it specifically, but because the data made its presence undeniable once processed through the right algorithms. Scientific discovery often unfolds in this manner. Instruments gather vast streams of data, and within those streams lie outliers that redefine the known landscape. Once W2246-0526 was identified, theoretical models faced a challenge. How could a galaxy generate so much energy so early in the universe's history? The prevailing view suggested a combination of intense starburst activity and accretion onto a central supermassive black hole. Yet the sheer scale of the luminosity exceeded expectations, pressing astrophysicists to refine models of gas inflow, radiation pressure, and galactic feedback. The object became not only a record holder, but a test case for theories of galactic evolution. The psychological resonance of discovery cannot be overlooked. When astronomers published results on W2246-0526, the reaction within the community carried the mixture of astonishment and unease that accompanies encounters with extremes. Extremes challenge categories, pushing the limits of what can be assimilated into existing frameworks. In human cognition, the encounter with extremes often triggers altered states, the sublime in art, the mystical in religion, the uncanny in psychology. In astronomy, extremes demand new theoretical scaffolding, but they also reverberate through culture, reshaping metaphors of light, power, and transience. The galaxy's distance adds another layer of intrigue. Observing it is not observing what it is, but what it was. Its light began its journey when Earth itself was unrecognizable, before life had emerged from single-celled ancestors. What we perceive is a fossil record in photons, carrying the imprint of conditions that prevailed long before our species could measure them. This delay between emission and reception parallels the delay in neural processing. The brain perceives events milliseconds after they occur, constructing a present that is already past. The cosmos scales this delay from milliseconds to billions of years, reminding us that perception is always a reconstruction, never direct immediacy. W2246-0526, once identified, became a beacon for further inquiry. Its discovery did not close a question but opened many. How could so much gas flow inward without being expelled prematurely? How stable can such a system remain under the assault of its own radiation? How many other galaxies, hidden by dust and awaiting the sensitivity of future instruments, burn with comparable or greater intensity? Each question extends the horizon of uncertainty, compelling deeper investigation and keeping the object suspended as a source of both illumination and unresolved tension. The raw output of W2246-0526 cannot be attributed solely to stellar populations, no matter how numerous or massive. At its core lies a phenomenon that transforms gravity into radiation with an efficiency unmatched by any nuclear process: accretion onto a supermassive black hole. This mechanism, though invisible directly, radiates with such ferocity that it reshapes the structure of entire galaxies, altering the flow of matter and determining their future development. A black hole, by definition, emits no light. Its event horizon marks the boundary beyond which no photon escapes. Yet paradoxically, the regions around black holes are among the most luminous in the universe. As interstellar gas drifts inward, gravitational potential energy converts into kinetic energy, and friction between turbulent streams of matter heats the accretion disk to extraordinary temperatures. These disks glow across the electromagnetic spectrum, producing radiation thousands of times more powerful than all the stars combined within the host galaxy. The light does not come from the black hole itself, but from the violence of matter resisting its fate, torn apart as it spirals inward. The physics of accretion requires a delicate balance. Gas and dust do not fall straight in. Angular momentum forces them into rotation, forming a flattened, turbulent structure. Magnetic fields threading through this plasma drive instabilities that redistribute angular momentum, allowing material to drift closer while some is flung outward. The dissipation of orbital energy through viscosity and turbulence generates heat that radiates away. In W2246-0526, this process occurs on scales so extreme that the entire galaxy becomes dominated by the emission of its nucleus. The energy released in accretion can reach efficiencies of 10 to 40% of the rest mass of the material consumed. By comparison, nuclear fusion within stars converts only 0.7% of hydrogen's mass into energy. This disparity explains why a single supermassive black hole, when fed with enough material, can eclipse billions of stars in luminosity. W2246-0526 demonstrates this efficiency on a scale that stretches astrophysical theory, demanding mechanisms capable of sustaining such inflows without immediate collapse of the system. Jets of relativistic plasma, often associated with active nuclei, provide further channels of energy release. While the central black hole in W2246-0526 has not been mapped in detail at radio wavelengths, analogous systems suggest that material channeled along magnetic field lines near the event horizon can be expelled at velocities close to the speed of light. These jets extend far beyond the galaxy, injecting energy into the intergalactic medium and influencing neighboring systems. Such processes demonstrate how localized gravitational collapse can project consequences on scales millions of light-years wide. Radiation pressure from the accretion disk exerts a powerful counterforce on the infalling gas. Photons scatter off electrons, imparting momentum and pushing outward. This sets a theoretical upper limit on how much material a black hole can accrete in steady state, known as the Eddington limit. For W2246-0526, sustaining its observed luminosity implies accretion near or above this limit, suggesting that the system operates in a precarious regime where inflow and outflow nearly cancel one another. The turbulence detected by ALMA in its carbon emissions confirms that gas within the galaxy is anything but stable. The psychological resonance of this energy transformation lies in its extremity, unseen collapse producing overwhelming radiance. In many traditions, from Hindu depictions of Shiva as both creator and destroyer to Christian visions of light pouring from apocalyptic revelation, brightness is inseparable from destruction. Cognitive scientists studying altered states note that imagery of radiant dissolution often accompanies near-death experiences or deep meditative absorption. In these states, the sense of self is drawn toward a center of intensity that both annihilates and illuminates. The physics of black holes mirrors this archetype with unsettling precision. Experiments in neuroscience show that overstimulation of sensory pathways can induce paradoxical silence in perception. When the retina receives an excess of photons, photoreceptors saturate, producing blindness rather than vision. Similarly, overwhelming auditory input can collapse into an absence of discernible sound. These effects resemble what galaxies like W2246-0526 embody at cosmic scale, systems so intense that their radiance undermines their own stability. The brightest output becomes the seed of disintegration. The relationship between energy and structure is fragile. Galaxies require gas to form new stars and sustain their stellar populations. Yet the outpouring of energy from an active nucleus can heat or expel that gas, depriving the galaxy of its raw material. In W2246-0526, observations indicate that gas clouds are being driven outward at thousands of kilometers per second, an exodus propelled by radiation pressure. This means the very force that fuels the galaxy's brilliance also erodes its capacity for future growth. The scale of these processes invites comparisons with human physiology. The brain, for instance, consumes approximately 20% of the body's energy, while comprising only 2% of its mass. High metabolic demand grants consciousness its power, but it also renders neural tissue vulnerable to fluctuations in oxygen or glucose. Just as the brain can collapse into seizure or unconsciousness when energy balance is disrupted, so can a galaxy destabilize when its central engine floods the system with excessive radiation. Both reveal a paradox. Concentration of power enhances function while simultaneously courting breakdown. When astronomers speak of galaxies as ecosystems, W2246-0526 becomes an extreme illustration of the metaphor. Energy cycles through inflow, transformation, and outflow, reshaping the environment with each stage. The balance is precarious, sensitive to initial conditions and feedback loops that magnify small disturbances into sweeping consequences. Such a system cannot remain static. It teeters between expansion and exhaustion, radiance and collapse, each moment carried forward by forces that strain against the possibility of stability. The sense of being cast out, even in symbolic form, penetrates deeper than conscious reasoning can easily counteract. The cyberball experiments demonstrate that a simple exclusion from a virtual game evokes neural pain signatures nearly indistinguishable from those triggered by physical injury. The dorsal anterior cingulate cortex, often termed the brain's alarm system, lights up when social bonds are threatened, while the anterior insula contributes the visceral ache that makes rejection feel not metaphorically but literally painful. Such findings reshape the understanding of suffering. Exclusion is not an abstract discomfort, but a neurobiological wound that leaves measurable traces in circuits of perception and emotion. Evolutionary explanations of this overlap suggest that in ancestral environments, social isolation was a dire signal, one often preceding starvation, predation, or death. The brain appears to have co-opted ancient nociceptive systems to ensure that individuals responded with urgency to signs of exclusion. What was once adaptive continues to influence modern life, where reputational slights or digital neglect can activate the same survival machinery as a broken bone. The fragility of relational bonds, encoded in these overlapping pathways, makes social belonging a matter of physiological as much as psychological necessity. Hormonal mediators bind these circuits to bodily states. Oxytocin, sometimes simplified in popular accounts as the bonding hormone, operates in far more nuanced ways. It modulates trust, enhances attention to social cues, and amplifies the salience of group membership. Elevated oxytocin levels have been shown to increase generosity in economic exchange tasks, yet they also heighten defensive aggression when an outgroup is perceived as threatening. This duality reveals that the chemistry of connection is not a unidirectional force toward harmony, but a finely tuned system of inclusion and exclusion, designed to bind some while distancing others. Vasopressin, a closely related neuropeptide, contributes additional layers to this relational architecture. In prairie voles, a species known for forming long-term pair bonds, the distribution of vasopressin receptors in the ventral pallidum correlates with the strength of attachment. Genetic manipulations that alter receptor density can shift behavior from monogamous bonding to promiscuity. Human parallels, though more complex, hint at similar mechanisms. Polymorphisms in vasopressin receptor genes have been associated with variations in relationship stability, suggesting that even intimate loyalty is partly scaffolded on molecular codes. The architecture of social pain and attachment also intersects with reward circuitry. The ventral striatum, which registers the anticipation of pleasure, responds robustly to images of loved ones, embedding relational ties within the same dopaminergic loops that reinforce food, shelter, or drug use. This entanglement explains why love and addiction share striking phenomenological similarities: obsessive focus, craving, withdrawal, and relapse. Neuroimaging studies of individuals recently rejected by romantic partners show activity in these same striatal regions, as if loss itself becomes a negative reward signal, pulling attention back to the absent figure with compulsive force. Such compulsions illustrate that the relational brain does not merely record interactions. It binds them into motivational loops that can dominate behavior. The anterior cingulate, insula, and striatum form a triad where social experience becomes somatic, emotional, and goal-directed simultaneously. When the system stabilizes, it produces trust, empathy, and collaboration. When destabilized, it fosters obsession, jealousy, or retaliatory aggression. The very circuits that sustain social life are also those that, when strained, magnify its dangers. Historical practices recognized this double-edged nature long before neuroscience provided anatomical confirmation. Exile was among the harshest punishments in ancient societies, regarded by Athenians as a fate nearly equivalent to death. Religious traditions often cast damnation in terms of exclusion from the communal presence, a symbolic stripping away of connection that mirrors the neural signatures of pain. The consistency of these themes across cultures points to an intuitive awareness that belonging is not optional ornamentation, but the structural core of human existence. The developmental trajectory of these systems reinforces their centrality. Infants deprived of consistent caregiving, as documented in studies of orphanages with low caregiver-to-child ratios, exhibit reduced gray matter volume in prefrontal and temporal regions critical for social cognition. Behavioral consequences include difficulties in attachment, heightened reactivity to stress, and long-term impairments in executive functioning. These findings underline that the absence of relational nourishment reshapes the architecture of the brain itself, leaving enduring marks on cognition and emotion. Yet even within healthy development, tension pervades the system. The same neural circuits that promote cooperation also track fairness with unforgiving precision. Experiments using the dictator game reveal that individuals observing unfair distributions exhibit amygdala activation, as though inequity constituted a form of threat. Punishing unfairness, even at personal cost, recruits the dorsolateral prefrontal cortex, linking moral judgment with executive control. In this way, the pursuit of justice emerges not as abstract philosophy, but as a biologically grounded impulse, inscribed in circuits evolved to safeguard cohesion. Music and rhythm, so central to group life, can be viewed as strategies for stabilizing these fragile balances. By synchronizing movements and vocalizations, groups align internal states, reducing the friction of hierarchy and difference. Neurochemical measurements show rises in endorphins and dopamine following synchronized drumming or singing, lending neurobiological substance to the ancient intuition that rhythm binds communities. Yet this synchrony, too, can be directed toward divergent ends. Chants can prepare warriors for battle as readily as they can elevate congregants in worship. The relational brain carries with it no guarantees of benevolence. Its machinery can construct bridges of empathy or walls of exclusion, often depending on subtle cues of identity, trust, and fairness. Once activated, these circuits steer perception and action with a force that resists conscious override. The same insula that generates compassion for a suffering neighbor may generate disgust at an outgroup member, each response born of identical mechanisms calibrated by context. Such volatility leaves open questions about the durability of social cohesion in environments where relational cues shift rapidly. Digital technologies multiply contacts but thin the embodied signals of voice, gesture, and proximity on which these systems depend. Neuroimaging of online interactions already suggests attenuated activation in areas normally engaged by face-to-face encounters. The brain's machinery, calibrated over millennia for the intimacy of small groups, now struggles to process social networks scaled to thousands. In this tension between ancient circuits and modern conditions lies a fault line whose consequences extend beyond individual well-being to the stability of entire societies. The fragility of ancient circuitry under modern conditions becomes more evident when considering the phenomenon of ambient social exposure. For most of evolutionary history, The number of individuals one might recognize and track rarely exceeded a few hundred. Robin Dunbar's comparative analyses of primate brain sizes and social groupings yielded an estimate near 150 for the cognitive ceiling of human social relationships, a figure echoed in anthropological records of village and clan sizes. Yet contemporary life routinely demands awareness of thousands of names, faces, and reputations, a scale that strains mechanisms tuned for intimacy and immediate reciprocity. Cognitive load increases when identities are mediated by symbols rather than embodied presence. Social media interactions strip away tactile, olfactory, and prosodic cues, leaving behind a reduced bandwidth of written words, images, and brief vocal fragments. Neuroimaging reveals that the fusiform face area, optimized for rapid recognition of live expressions, responds less vigorously to static images or avatars. The amygdala, which calibrates trustworthiness judgments from microexpressions, receives impoverished data streams, making its evaluations less reliable. The mismatch generates a peculiar combination of overexposure and underperception. Many signals, few certainties, constant demand for interpretation. This mismatch has consequences for regulation of stress. Cortisol rhythms, shaped in part by synchrony with others, falter when interactions lack the embodied cadence of turn-taking and physical presence. Studies on adolescents who spend prolonged hours in digital environments show altered diurnal cortisol slopes, resembling patterns seen in chronic stress conditions. Such dysregulation may account for heightened rates of anxiety, disrupted sleep, and difficulty with sustained attention, all of which trace back to the brain's difficulty reconciling ancestral needs for embodied communion with abstracted streams of symbols. At the same time, novelty engages reward pathways. Dopaminergic surges accompany each notification, each unpredictable cue of social relevance. The striatum, sensitive to reward prediction errors, fires when a message arrives unexpectedly, reinforcing the behavior of constant checking. The architecture that once tuned vigilance to the subtle approach of an ally or rival now trains itself on glowing screens, awaiting the next digital trace of approval or threat. What was adaptive vigilance risks becoming compulsive vigilance, cycling in loops that erode reflective control. Cultural anthropology provides a parallel record of how ritual sought to stabilize these circuits. Communal rites of passage, seasonal gatherings, and storytelling sessions imposed rhythms on social life, bounding interactions within predictable patterns. The repetition of chants, the regulated timing of feasts, and the codification of myths served to align neural states across participants, anchoring meaning in shared sequence. Without such pattern scaffolding, interactions risk becoming fragmented, their cues too fleeting to register as stable bonds. The loss of ritual in modern contexts strips away these regulatory frames, leaving individuals more exposed to the volatility of unstructured signals. The plasticity of the social brain means that such exposures recalibrate perception itself. Habituation occurs when repeated signals, even impoverished ones, become the default environment. Eye tracking studies indicate that individuals who spend significant time with digital imagery scan faces differently in real encounters, focusing more on the mouth than on the eyes, perhaps reflecting adaptation to emoji-like shorthand rather than nuanced gaze patterns. Over time, these micro-adjustments may reshape the efficiency of circuits once specialized for subtle inference, bending them towards simpler, more schematic interpretations. The consequences of this recalibration extend into domains of memory and identity. Autobiographical recall is heavily scaffolded by social confirmation, the retelling of events, the reinforcement of narratives by others. When memory is increasingly externalized into digital records, likes, and algorithmic reminders, the hippocampus receives fewer demands to integrate experiences into coherent temporal sequences. Studies using fMRI have observed reduced hippocampal activation during tasks of episodic recall among heavy digital archivists, suggesting that external scaffolding shifts the burden away from internal consolidation. What appears as convenience may conceal a trade-off. The outsourcing of memory to external devices erodes the circuitry that once guaranteed continuity of self. Moral judgment is likewise reshaped by these conditions. Exposure to vast and rapid streams of information, much of it anonymized, confronts the anterior insula and amygdala with an unrelenting sequence of potential violations. Yet without embodied cues, the visceral resonance of disgust or compassion may be blunted, producing a paradoxical mixture of hypervigilance and desensitization. Experiments comparing reactions to live testimony versus written reports of injustice show markedly greater activation in limbic regions during live interaction, suggesting that mediated forms attenuate the visceral grounding of moral response. A flattened moral effect, spread across endless fragments, may reduce the capacity for sustained ethical commitment. Collective movements that emerge in digital spaces illustrate another aspect of these shifting dynamics. Entrainment, once dependent on physical synchrony of bodies, now occurs through symbolic synchrony of repeated phrases, hashtags, or viral sounds. The temporal coupling observed in face-to-face speech finds its analogue in the near-simultaneous adoption of slogans across dispersed populations. While these forms can generate rapid cohesion, they lack the stabilizing depth of embodied rituals. The synchrony may ignite swiftly but dissipates with equal speed, leaving behind cycles of intensity that flare and fade without integration. The adaptability of the brain ensures that these conditions do not merely overwhelm, they also produce novel configurations. Neural networks reweight connections, privileging speed over depth, breadth over nuance. Yet each recalibration carries hidden costs, for what is gained in efficiency of signal processing may erode the fine-grained attunement required for trust, intimacy, and enduring cooperation. The unresolved question is whether these adjustments represent temporary plastic shifts or enduring transformations of relational architecture itself. The trajectory remains unsettled, caught between the brain's ancient scaffolds and its modern exposures. Circuits built for embodied synchrony now face an environment of fragmented cues, intermittent reinforcements, and accelerated scales. The question pressing against the limits of neuroscience is not only how these circuits adapt, but what kinds of selves and societies emerge when adaptation itself becomes a condition of perpetual strain. The strain of adaptation becomes most visible in the domain of attention. Neural systems designed to oscillate between focused engagement and diffuse monitoring now confront an environment that compresses both into continuous bombardment. The locus coeruleus, regulating norepinephrine release, orchestrates these shifts by modulating arousal states. Under natural conditions, it balances bursts of high precision with periods of exploratory scanning. Yet when cues arrive incessantly, this balance falters, leaving the system in a state of chronic microarousal. The result is neither deep immersion nor restful openness, but a jittering instability that exhausts cognitive resources. The prefrontal cortex, tasked with maintaining goal representations, struggles under such volatility. Working memory traces are disrupted by each novel stimulus, a phenomenon confirmed in electrophysiological studies showing attenuated P300 signals during task performance in high-notification environments. The brain, in effect, rehearses abandonment of sustained focus, training itself to treat interruption as the baseline. This reconfiguration reshapes not only productivity but identity itself, for the self is partially composed through narratives that require temporal continuity. Fragmentation of attention risks fragmentation of selfhood, an erosion occurring beneath conscious awareness. Sleep provides another lens onto these pressures. The consolidation of memory and emotional regulation during slow-wave and REM cycles depends on rhythmic oscillations of hippocampal and cortical networks. Yet exposure to late-night digital cues delays circadian rhythms, suppresses melatonin release, and fragments sleep stages. Polysomnographic studies of individuals with high nocturnal device use show reductions in slow-wave activity, impairing the integration of new experiences into stable memory traces. Dreams, often theorized as a theater for emotional recalibration, become truncated, leaving residues of unprocessed effect that bleed into waking states. The immune system is not exempt from these patterns. Chronic low-level stress, mediated by disrupted cortisol regulation, weakens immune responsiveness. Pro-inflammatory cytokines rise in tandem with irregular sleep and fractured attention, contributing to fatigue, mood disturbances, and heightened vulnerability to illness. The body becomes a mirror of strained circuits, registering the costs of social and cognitive overload in tissues far removed from the brain. Such findings blur the distinction between psychological and somatic health, revealing them as expressions of the same relational system under duress. The vulnerability is magnified in developmental contexts. Adolescents, whose prefrontal cortex remains in prolonged maturation, show heightened sensitivity to social evaluation. Functional MRI studies demonstrate exaggerated ventral striatum activation when receiving online approval signals, while rejection elicits stronger responses in the anterior cingulate compared to adults. These responses sculpt neural trajectories that set the tone for later emotional regulation. Environments saturated with intermittent reinforcement risk, embedding patterns of craving and aversion into the architecture of identity before reflective control has matured. Cultural history reveals earlier analogues of overstimulation, though in slower rhythms. Urbanization in the 19th century provoked concerns over nervous exhaustion and neurasthenia, conditions described by George Beard as consequences of accelerated communication, industrial machinery, and crowded social spaces. Though framed differently, these accounts resonate with present neurobiological findings. Circuits attuned to slower cycles of attention, rest, and ritual faltered under relentless novelty. The recurrence of such concerns suggests that technological expansion repeatedly outpaces neural adaptation, producing recurrent syndromes of strain. Yet overstimulation does not always manifest as collapse. It can also generate altered states. Prolonged exposure to repetitive stimuli, whether rhythmic drumming, chanting, or even continuous digital scrolling, can induce trance-like absorption. Neuroimaging of meditative and hypnotic states shows reduced activity in the default mode network, particularly the posterior cingulate cortex, associated with narrative self-construction. Similar reductions have been observed in subjects deeply absorbed in immersive media. The self loosens its boundaries, and perception narrows into the stream of repetitive signals. What is pathologized as distraction in one context may function as absorption in another, illustrating the malleability of attentional systems. The ambiguity of these states complicates evaluation. Trance can provide relief from self-referential rumination, offering calm and unity, but it can also render individuals more susceptible to suggestion, less critical of incoming signals. The fine line between liberation and vulnerability lies in the same circuitry, depending on whether the external environment stabilizes or exploits the entranced state. Societies have long recognized this ambivalence, embedding trance in rituals of healing while fearing its potential for manipulation. The neural evidence now confirms what myth and tradition intuited: altered attention is both medicine and weapon, contingent on its framing. Neurochemical pathways offer insight into this duality. Gamma-aminobutyric acid, GABA, the brain's chief inhibitory transmitter, increases during meditative absorption, quieting cortical chatter. Dopaminergic surges, meanwhile, reward the novelty or rhythm that holds attention. When balanced, these systems cultivate focus and calm. When distorted, they foster compulsion. Digital environments exploit this balance, delivering rhythmic novelty that sustains dopamine release without providing the embodied anchors that normally stabilize absorption. The individual floats between craving and sedation, caught in a cycle neither fully restful nor fully satisfying. This delicate interplay raises broader questions about the thresholds of human attention. How much novelty can circuits sustain before coherence unravels? How much rhythm is required to stabilize the self without dissolving it into trance? These questions are no longer abstract but immediate, as societies organize work, leisure, and politics around platforms designed to test such thresholds continuously. Each notification, each algorithmic suggestion, is not merely information but a probe into the elasticity of neural systems. The pressures accumulate silently, shaping perception, memory, and emotion in ways that rarely surface to conscious awareness. Beneath the ordinary routines of checking, scrolling, and responding, circuits recalibrate, identities adjust, and societies tilt toward patterns no single individual intends. The trajectory of these changes points toward outcomes not yet fully mapped, suspended between resilience and fracture, adaptation and overload. The vulnerability of attention under continuous strain extends into the perception of time itself. Temporal experience, long regarded as a stable backdrop, is increasingly revealed as a construct shaped by neural oscillations and attentional rhythms. The suprachiasmatic nucleus anchors circadian cycles to light cues, but the subjective flow of time depends on dopaminergic modulation in the basal ganglia and prefrontal cortex. When novelty accelerates, dopamine surges shorten subjective intervals, making minutes feel compressed. When monotony dominates, reduced dopaminergic tone elongates them, stretching seconds into apparent immobility. In digital environments, the alternation of hypernovelty and monotony creates a disjointed sense of time, fragmenting continuity into unpredictable stretches and compressions. Experimental work on temporal illusions demonstrates the pliability of these perceptions. The oddball paradigm, where a novel stimulus appears among repeated ones, reliably produces a temporal dilation effect. The novel item seems to last longer than its actual duration. In natural settings, each digital notification functions as such an oddball, distorting the felt passage of time by magnifying its salience. Over prolonged exposure, these distortions accumulate, leaving individuals uncertain whether hours have vanished in an instant or dragged on with oppressive slowness. This instability undermines the construction of coherent narratives, for continuity of self relies on temporal scaffolding as much as spatial context. Alterations in temporal perception reverberate in emotional regulation. The amygdala calibrates fear responses partly by estimating the imminence of threat. Accelerated subjective time can exaggerate danger, while slowed perception may dull urgency. Stress hormones interact with these distortions, amplifying anxiety when moments feel compressed beyond control. Clinical observations of panic attacks often describe a sense that time itself is accelerating uncontrollably, a subjective correlate of heightened amygdala and sympathetic activity. Conversely, depressive states are frequently associated with temporal slowing, where future events recede beyond reach, an experience mirrored by reduced striatal dopaminergic signaling. Cultural practices have long sought to regulate time perception through structured rhythms. Religious rituals impose predictable temporal markers, daily prayers, weekly gatherings, seasonal fasts, which recalibrate subjective flow by anchoring it to communal cycles. Music operates similarly, aligning internal oscillations with external beats. Studies using electroencephalography show that rhythmic entrainment can synchronize neural oscillations across participants, effectively creating shared temporal scaffolds. Such synchronization not only regulates emotion but fosters cohesion, reminding the brain that its subjective time is part of a larger communal rhythm. The loss or distortion of these scaffolds in modern environments leaves individuals increasingly dependent on artificial markers. Digital clocks, reminders, and algorithmic prompts substitute for embodied rhythms, yet they lack the effective depth of communal rituals. The brain registers the schedule but does not feel its weight, leaving a gap between abstract measurement and lived duration. This gap contributes to the pervasive sense of disorientation in contemporary life, where days feel simultaneously overcrowded and empty, swift and stagnant, measurable yet ungraspable. The hippocampus, central to episodic memory, provides another angle on this erosion. Its place and time cells encode experiences within spatial temporal contexts, enabling coherent recall. When experiences lack variation or embodied engagement, hippocampal firing patterns become repetitive, leading to weaker memory consolidation. This phenomenon has been documented in laboratory settings where subjects confined to uniform environments report poor recall of duration and order. In modern life, scrolling through uniform streams of stimuli replicates such monotony at scale, dulling the hippocampal encoding of temporal boundaries. The result is a blurring of days into indistinct stretches, a lived amnesia of sequence. The vulnerability of temporal construction also carries implications for identity. Narrative psychology emphasizes that selfhood emerges through the sequencing of events into a coherent story. If time fragments, narrative coherence falters, leaving individuals with collections of moments insufficiently integrated into meaning. Neurobiological correlates of this fragmentation can be seen in disruptions of the default mode network, which normally integrates past, present, and imagined future into unified perspective. Functional connectivity studies reveal that weakened coupling between medial prefrontal and posterior cingulate regions correlates with diminished autobiographical coherence, a state subjectively reported as disorientation or emptiness. Extreme cases illuminate the stakes. Psychedelic states, for example, frequently alter temporal perception, sometimes producing experiences of timelessness or infinite duration. Neuroimaging links these states to disintegration of oscillatory synchrony across cortical regions. While such alterations may yield insights or relief, they also reveal how fragile the construction of temporal flow truly is. Less dramatic but more insidious are the daily microdistortions induced by overstimulation, gradually bending the subjective fabric of time without conscious awareness. The consequences of such bending extend into social coordination. Trust and cooperation rely on shared expectations of timing. When a partner will respond, how long a task should take, when an obligation becomes overdue. Disrupted time perception destabilizes these expectations, producing mismatched rhythms that strain relationships. Experimental studies in dyadic interaction show that even slight asynchronies in conversational turn-taking increase perceived awkwardness and reduce feelings of rapport. In larger groups, these mismatches scale into systemic inefficiencies, as coordination falters without reliable temporal anchors. At the biological level, attempts to recalibrate often take maladaptive forms. Stimulants artificially accelerate subjective time, offering bursts of focus at the cost of rebound crashes. Depressants slow it, granting temporary relief but risking lethargy and dependence. These chemical interventions mimic natural oscillations, but without the embedded social rhythms that normally stabilize them. The result is fragile control, vulnerable to collapse under stress, leaving individuals oscillating between hyperacceleration and stagnation. The unresolved question is how circuits designed for steady temporal scaffolding will adapt to environments that fracture duration so persistently. Whether the brain can generate new forms of coherence from these fragments, or whether it succumbs to progressive disorientation, remains an open tension. The trajectory unfolds not only in laboratories but in everyday life, as individuals struggle to hold narrative continuity against the distortions of accelerated novelty and suspended monotony. Disorientation in temporal flow carries implications beyond individual psychology, extending into the fabric of collective decision-making. Societies operate on shared assumptions of duration: how long growth cycles require, how quickly justice should be delivered, how swiftly dangers must be met. When subjective time fragments, the capacity to sustain long-range coordination falters. Political impatience, economic speculation, and cultural volatility can be traced to neural systems no longer anchored in coherent duration. Decisions once guided by seasonal rhythms or generational continuity increasingly bend to the immediate tug of novelty. The economic domain reveals this distortion vividly. Financial markets thrive on microsecond fluctuations, an acceleration far removed from the biological pacing of human cognition. Traders describe states of heightened absorption in which minutes seem compressed, with entire fortunes gained or lost before awareness has caught up. Neuroimaging of individuals engaged in high-frequency trading shows intensified striatal activation, reflecting reward anticipation, while prefrontal areas display signs of overload. The mismatch between circuitry evolved for foraging decisions and environments demanding millisecond precision illustrates how collective systems amplify neural vulnerabilities into systemic risks. Law and governance also depend on shared temporal scaffolds. Justice, in many traditions, is described as requiring patience, deliberation, and measured pacing. Yet digital communication demands immediate responses, reducing tolerance for delay. Citizens habituated to instant access grow restless with institutions whose processes unfold across years. The anterior cingulate cortex, attuned to conflict and expectancy violation, fires when anticipated responses lag, translating bureaucratic delay into felt frustration. In such climates, pressure builds to accelerate decision-making, risking shallow evaluation and volatile policy. Cultural life, too, reflects the recalibration of time. Art once unfolded in prolonged encounters, the hours required to read a novel, the lingering immersion of symphonic performance. Contemporary consumption increasingly favors fragments, compressed into loops and clips measured in seconds. This compression reshapes attention, but also alters aesthetic expectation. Brain regions engaged in sustained narrative integration, including the posterior cingulate and medial prefrontal cortices, receive less stimulation, while salience networks respond to rapid novelty. The long arc of interpretation gives way to bursts of impression, shaping not only taste but the architecture of imagination itself. Memory's role in shaping collective identity also falters under these conditions. Commemoration rituals once stabilized narratives across centuries, anchoring societies in durable continuity. Yet accelerated communication floods attention with ever-new content, displacing older memories before they can consolidate into cultural bedrock. Neurobiological parallels emerge in studies of working memory interference, where new inputs overwrite traces of recent ones. At the societal scale, this dynamic manifests as historical amnesia, where events lose salience not through censorship but through sheer acceleration of novelty. Religious traditions offer instructive counterpoints. Pilgrimage, fasting, and Sabbath practices slow the perception of time deliberately, creating sanctuaries from acceleration. These practices re-engage the body's natural rhythms, aligning cortisol cycles, heart rate variability, and communal synchrony. Anthropological records describe how such intervals recalibrate collective attention, binding groups across generations. Neuroimaging of contemplative states supports these observations, showing restored connectivity in networks that integrate temporal continuity. Such practices reveal that societies have long intuited the fragility of time perception and sought to stabilize it through ritual. Yet ritual itself can be manipulated. Authoritarian regimes often engineer mass gatherings, marches, or synchronized spectacles designed to bend temporal experience. By saturating attention with choreographed rhythms, they suppress individual pacing and impose collective tempo. The brain, responsive to synchrony, entrains willingly, generating powerful feelings of unity that blur personal boundaries. Studies of crowd dynamics show surges of endorphins and dopamine during synchronized chanting, explaining the intoxicating sense of belonging. But this unity, produced by manipulation of time and rhythm, also suppresses critical judgment, leaving individuals vulnerable to suggestion. The vulnerability of temporal construction extends into trauma. Individuals exposed to overwhelming events frequently describe time as frozen, accelerated, or fragmented. Neurobiological studies link such distortions to amygdala hyperactivation and hippocampal disruption. Traumatic memories often return not as coherent narratives, but as intrusive fragments, stripped of temporal sequence. The brain's inability to situate these fragments in chronological order perpetuates re-experiencing, as if the past erupts continuously into the present. At the collective level, societies that undergo war, famine, or catastrophe exhibit similar disruptions, with cultural memory fractured into competing fragments that resist integration. Emerging technologies increasingly probe these vulnerabilities. Virtual reality environments manipulate temporal flow by altering frame rates, narrative pacing, and sensory immersion. Users report distortions of duration, sometimes underestimating time spent by significant margins. Neurophysiological studies reveal altered patterns of theta oscillations in the hippocampus during immersion, correlating with these subjective shifts. The capacity to engineer temporal perception at will raises profound questions about agency, identity, and control. What was once the province of ritual or accident becomes a programmable variable in the design of experience. These manipulations expose a fault line between natural resilience and engineered fragility. The brain's plasticity allows adaptation, but adaptation comes with trade-offs. Enhanced responsiveness may cost coherence, while increased speed may erode depth. The trajectory of these trade-offs remains uncertain, suspended between enrichment and depletion. What emerges in this liminal space is neither collapse nor stability, but a condition of heightened susceptibility, where identity, memory, and cohesion depend on rhythms no longer entirely under human control. The unresolved tension lies in whether the neural architectures that construct duration can sustain coherence under conditions of perpetual acceleration and fragmentation, or whether they drift toward thresholds beyond which narrative continuity disintegrates. As the pressures accumulate, the very definition of what it means to inhabit time begins to shift, leaving open the possibility of transformations whose consequences have yet to be measured. The instability of temporal construction intersects with perception of space, for both dimensions are inseparably linked in neural encoding. The hippocampus, with its dual networks of place and time cells, weaves moments and locations into coherent trajectories. When time falters, spatial maps lose precision, and when space becomes abstracted, temporal flow unravels. Modern environments compound this fragility by eroding embodied navigation. GPS technologies replace wayfinding with automated instructions, bypassing hippocampal circuits that evolved to bind movement, memory, and orientation. Longitudinal studies reveal measurable reductions in hippocampal gray matter among heavy GPS users, suggesting that outsourced navigation reshapes neural architecture at structural levels. This outsourcing carries implications for autonomy. The experience of moving through the world with self-generated maps fosters confidence and agency, embedding memory into the very act of orientation. When spatial processing is externalized, the individual inhabits a thinner reality, guided by signals detached from embodied exploration. Such reliance subtly shifts the boundary between self and environment, leaving cognition vulnerable to the rhythms of devices that dictate where to turn, when to stop, how to arrive. The brain registers the route but no longer constructs the story of the journey, severing memory from motion. Urban design intensifies this process. Environments dominated by uniform grids, anonymous towers, and repetitive signage deprive the hippocampus of the varied cues required for robust mapping. Research on environmental enrichment demonstrates that animals raised in monotonous settings show reduced dendritic branching and impaired spatial memory compared to those exposed to complex, varied habitats. Human parallels emerge in studies linking suburban monotony to disorientation, stress, and diminished attachment to place. When environments lack distinctive features, they fail to anchor memory, leaving inhabitants adrift in spaces that blur into one another. The absence of anchor points undermines not only orientation but also identity. Place attachment, rooted in neural associations between location, memory, and emotion, serves as a stabilizer of self. Sacred landscapes, ancestral homes, or even familiar neighborhoods provide continuity by embedding personal narratives in enduring geography. When displacement occurs, whether through migration, gentrification, or disaster, the severing of these bonds destabilizes selfhood. Neuroimaging reveals that recalling familiar places activates medial prefrontal regions tied to autobiographical memory, illustrating that place is not external context but internal scaffolding. When place dissolves, so too does a layer of self. At collective scales, spatial disorientation disrupts cohesion. Traditional societies often marked boundaries with sacred groves, rivers, or monuments, embedding social order in geography. Modern expansion frequently erases such anchors, replacing them with transient structures that lack symbolic depth. Anthropological accounts describe how this erasure generates what Mark Orgy termed non-places. Airports, shopping malls, highways, spaces designed for circulation rather than dwelling. Neuroscientific studies of individuals in such environments reveal heightened amygdala activity, suggesting vigilance without attachment. One moves through the space but never belongs to it. The psychological cost of non-places is amplified by their temporal qualities. Airports collapse time zones, malls abolish day-night cycles, highways stretch distance into endless monotony. The brain, deprived of natural temporal spatial markers, slips into dissociation, a state in which perception continues but coherence falters. Functional imaging of dissociative states indicates reduced integration between prefrontal and limbic regions, as if the mind detaches from the body's coordinates. In such states, agency becomes fragile, leaving the individual more suggestible, less anchored, more adrift. Historically, rituals of orientation counterbalanced these risks. Indigenous traditions often embedded navigation in songlines, myths, or star maps, integrating geography with cosmology. These practices preserved not only routes but meaning, linking each landmark to story and significance. By engaging hippocampal and prefrontal circuits simultaneously, they stabilized both spatial and narrative identity. Modern substitutes, by contrast, reduce navigation to coordinates and efficiency, stripping away layers of meaning. The journey becomes mechanical, the destination abstract, the path forgotten as soon as it is traversed. This erosion of spatial-temporal anchoring invites reflection on vulnerability to manipulation. When individuals no longer construct their own maps, they depend on external systems whose rhythms and motives may not align with personal or collective well-being. Algorithms that guide movement, recommend destinations, or predict preferences subtly reshape patterns of dwelling and interaction. Over time, neural pathways adapt to these imposed rhythms, bending perception of space and time toward architectures not self-chosen. The possibility emerges that autonomy itself can be redirected, not through coercion but through imperceptible shifts in orientation. The fragility of these systems is further exposed in conditions of crisis. Natural disasters, forced displacement, or technological collapse reveal how dependent cognition has become on external scaffolds. When GPS signals fail or familiar landmarks vanish, individuals experience profound disorientation, sometimes bordering on panic. Neurobiological studies show surges in stress markers when navigational certainty collapses, as the hippocampus and amygdala engage in frantic recalibration. The thinness of modern anchoring is laid bare, revealing how shallowly the self is rooted in environments stripped of enduring orientation. What emerges is a precarious balance. The brain's ancient machinery for weaving space and time into coherent maps is increasingly bypassed by external systems that promise efficiency while eroding depth. The cost is not immediate collapse but gradual reshaping, a reconfiguration of circuits, identities, and attachments that leaves the individual both capable and vulnerable, oriented and unmoored. The trajectory of these shifts continues to unfold, carrying with it unresolved tensions between autonomy and dependence, coherence and fragmentation, memory and forgetting.